Hello. Our lesson of today, we shall be speaking about the derivative of inverse and composite and implicit functions. Now, in the last lecture, the one that we gave on differentiation, we established the definition of differentiability and the existence of the differentiation or the derivative of a function. But then what we investigated, as a matter of fact, were functions that are called explicit. In other words, usually you have the function in the form of y is equal to f of x. But this doesn't happen all the time. Sometimes you have composite functions. Functions do not occur in the form of sine x, for example. But you may encounter, for example, sine the square root of x. Now here you have a composite function, the square root of x and of sine x. You can also find functions in the form which is called implicit, not necessarily explicit. F of x in the form f of x and y equal to 0. The circle, for example, the equation of a circle is in explicit form, is in implicit form. So we have to investigate such forms of functions other than the explicit ones we already dealt with. So today we shall be speaking about the derivative of inverse composite, as I said, and implicit functions. And first of all, we shall deal with the derivative of the inverse function and what's the relation between the inverse function and the already known function f given. This we have already studied or taught, but this time we shall be concerned with the derivative of the inverse in relation to the derivative of the original function. Now, and then we shall be speaking about the derivative of composite functions, and here we shall be stating a rule called the chain rule, and this rule deals with such cases where the function is in the form which is in a composite, put into a composite form of two functions. Then we shall be speaking about the derivative of implicit as well as parametric functions. And then finally we shall end with when you have more than one derivative. In other words, you want the derivative of a derivative, and where do they exist and how can we deal with that. Now, to start with the derivative of an inverse function, before that, in our seventh lesson, we spoke about the inverse function, and we said inverse functions, they represent functions on your calculator, and this is the best way to comprehend such functions, is that you have an operation on your machine, and this operation, the contrary of this operation, is called the inverse function. For example, x squared and square root of x, these are inverse to one another, the exponential and the logarithmic as well. But this time here we shall be concerned with not the inverse operation, but the derivative of this such an inverse operation. So when you have, for example, a function of this sort, f of x is equal to x squared minus 3, this is a curve of a parabola, and you wish to calculate the derivative of such the derivative of this function, then it's easy. Since this is a power function, the derivative is equal directly to 2x. But then you wish to calculate the derivative of the inverse function. Now, the inverse function of this function is what? All you have to do, you get x as a subject in terms of y. Y is equal to x squared minus 3, and therefore x is equal to the square root of y plus 3. And here you have y greater than or equal to minus 3, since x is greater or equal to 0. And you wish to calculate the derivative of x in terms of y. Now, what you do, you have different options. Now, the first one, which is the easiest and straightforward, all you have to do is that you get the inverse function. You have here x squared minus 3. X squared minus 3, this is not an injective function because you have two branches of the function, so you have to choose one. So we chose the one which is the easiest, when x is greater than or equal to 0. Now, for this here, y would be greater than or equal to minus 3. This is the range of this function. So the inverse function would have this domain, greater than or equal to minus 3, whereas the range it would be greater than or equal to 0. Here is the inverse function. Directly, x is equal to the square root of y plus 3, and you want dx by dy. This is the derivative of the inverse function with respect to y at a point which exists in the domain of the inverse function. In other words, in the range of the original function. So what you do, straightforward, you differentiate this function and you substitute at y is equal to 1 at y is equal to 1, this corresponds to the value of x is equal to 2. So 2 and 1, this is an ordered pair where 2 lies in the domain of f and 1 lies in the range of f. And here you want to calculate dx by dy at the point y is equal to 1. So the derivative of y plus 3 to the power to the power half is equal to half y plus 3 to the power, this is a power function, half minus 1, so you get 1 over 2 square root of y plus 3. And after that, you substitute y is equal to 1 to obtain 1 over 4. So 1 over 4 represent the slope of the tangent of the inverse function at the point y is equal to 1. Here it is. This is the original function, y is equal to x squared minus 3, and the domain of which is all values of x greater than or equal to 0. So, of course, the range of the inverse function would be those values of x greater than or equal to 0, whereas here you have the range from minus 3 to infinity. So here the domain of your inverse function will be from the closed interval from minus 3 to infinity. Now, this function here, the derivative of which is equal to 2x, at the point 2 gives 4. So the derivative of your original function at the point 2, which lies in the domain of the function f, is equal to 4, whereas the slope of the tangent of the inverse function or the graph, the slope of the tangent at the point on the graph of the inverse function, at the point now y is equal to 1, which lies in the domain of the inverse function, will be equal to 1 over 4. And as a matter of fact, you find here that they are reciprocal to one another. This is 4 and this is 1 over 4. If this is 5, this is 1 over 5, etc. So here this is your inverse function. And it's not necessary that you find the inverse function in the form y is equal to square root of x plus 3. It's not necessary to have so, because here this is still an inverse function. The idea is that the operation itself, as we said before, this is squaring of x, and this is taking the square root. So these are two operations that are inverse to one another. And you have here the slope is equal to 1 over 4. Now the inconvenience here, difficulty here is that you have to find first the inverse function. Because from here you have to solve x in terms of y to obtain the inverse function, and then you differentiate x with respect to y. But sometimes you cannot do so. You cannot, and we said this before in one of our lessons, you cannot, for example, obtain x of an implicit function. You cannot solve x in terms of y sometimes to isolate the variables together. So here it's easy because the function is simple. So it was possible for you to isolate x in terms of y. But if you can't, then we have to rely on a theorem, and this theorem relates the derivative of the inverse function together. It relates it to the derivative of the original function. So here we can read it. If f is differentiable at a, its inverse function f minus 1, if it exists, it is differentiable at f of a. And we said before, for a function to have an inverse, it has to be injective. That's the most important thing, together of being, of course, surjective, but this is not important. We can restrict the codomain to the range of the function, and we can deal mainly with injective functions. So if f is injective, then it has an inverse, and this inverse is f minus 1. Now, if f, you know that it has, for example, it's monotonic increasing, so is f minus 1, and therefore you can obtain the derivative of f minus 1. How? From the relation, which is here, df minus 1 of y at the point y is equal to f of a, lying in the domain of the inverse function, is equal to 1 over df by dx at a point existing in the domain of the original function. So this can be written in a simple way. They usually write it in this way: dx by dy at the point y is equal to f of a is equal 1 over dy by dx at the point x is equal to a. This is the form that we encounter all the time. Now we can actually explain it here. Now what you have here, the function f, which maps a into f of a. You have here x and you have here y. You have here y, and then here y is a function of x, and here x again is a function of y in the form x is equal to f minus 1 of y. So when you need to calculate dx by dy at the point f of a lying in the domain of f minus 1, it is equal to 1 over dy by dx at the point a, which exists in the domain of the function f. In other words, you do here, it's nice to exhibit the operation, or to show the operation here, because it shows you that the operation are two ways. The derivative of a function here with respect to this is equal to the derivative of the other function with respect to a. So now we go back to the example we have just showed. Without calculating the inverse function, in this example, which is y is equal to x squared minus 3, we calculated the inverse function and then we differentiated. Now we don't want to calculate the inverse function. We just want to calculate the derivative directly from this theorem, which relates directly the derivative of the inverse function in relation to the derivative of the original function. So we use the theorem. So we have here d by dy of f minus 1 of y at the point 1, which exists in the domain of f minus 1, is equal to 1 divided by d by dx of the original function at the point 2, which lies in the domain of the original function. So when you differentiate this, you get 2x at 2 is equal to 1 over 4. So here we did not calculate f minus 1 in order to differentiate it, but we used the theorem directly in order to apply it and obtain the derivative of the inverse function. Now, in this example, this is another example, and in this example, we have no choice. Why? Because we cannot isolate x in terms of y. This is difficult here. Of course, this is given here. You want to calculate dx by dy at y equals to 2. Now, if y is equal to 2, x is equal to 1, which means that 1 exists in the domain of f, and 2 exists in the domain of f minus 1. In other words, the ordered pair, 1 and 2, 1 in the domain of f and 2 in the range of f. So here we cannot, it would have been much easier had we been able to calculate x in terms of y and differentiate it, but we can't here. So what we can do directly to obtain dx by dy is to resort directly to the theorem. So you get here dx by dy at y is equal to 2 is equal to 1 divided by d by dx of the original function at the point x is equal 1 in its domain. So you differentiate and you get 1 over 5. So without calculating the inverse function, you go ahead and calculate the derivative of this inverse function. Now sometimes, usually, the inverse function is not given in the form of f minus 1 of y. It's written in the form of f minus 1 of x. For example, you have y is equal to logarithm of x. Is logarithm of x is the original function or the inverse function? No, this is the inverse function, and the original function is e to the power x. So instead of writing y is equal to the e to the power x, and x becomes equal to logarithm of y, and this is the inverse function, which rightly it is, no, we shall consider that x is the point that lies in the domain of the inverse function. So we use an alternative formula. The same formula, except that we replaced the variable, we substituted the variable with one another. So in fact here now x becomes the point lying in the domain of f minus 1, whereas here y is the point lying in the range of f minus 1 or in the domain of f. So now you have what? You have a lying in the domain of f minus 1, and f minus 1 of a lies in the range of f minus 1. So you get the same formula in a different way. So d by dx of f minus 1 of x at x equal to a is equal to 1 over d by dy of f of y at y is equal to f minus 1 of a. And we can actually show this here. Now here, instead of writing here x and here y, no, because usually you wish to calculate, for example, the derivative of sine minus 1 of x, which is the inverse function of the sine, or the logarithm of x, or any function that is opposite or reciprocal or inverse to another function. And it's given in the form of explicitly y is equal to f of x. So you here, if you have, for example, this is the point x, which is a, then, and this is operating upon by the function f minus 1, so the other here point, which lies in the range of f minus 1, becomes equal to f minus 1 of a. So what we say now, df minus 1 of x with respect to x at the point a is equal to what? df1 over df by dy substituted into by y is equal to f minus 1 of a. Like this. I mean, it's both ways. Either you say the derivative of this with respect to y is equal to 1 over the derivative of f, 1 over the derivative of f with respect to x, Or you can say, you can write this x, and the derivative of f minus 1 with respect to x is equal to 1 over the derivative of f of y with respect to y at the point y, which is equal to f minus 1 of a. So let us take an example. Y is equal to ln x. We shall assume that ln x is the inverse function, and you want to differentiate it at the point x lying in its domain, which is all values of x greater than 0. So what you do is the following. You say dx dy by dx. Now it's not dx by dy. Dy by dx because you have f minus 1 of x. Dy by dx at the point x lying in the domain of f minus 1 is equal to 1 over d by dy of f. Where is f here? It's the original function, which e to the power y. At a point lying in the range of f minus 1, which is y is equal to ln x. When you do this, you got 1 over the derivative of e to the y is e to the y. You substitute y is equal to ln x, and you get 1 over e to the power ln x. But you know very well that the exponential and logarithm are reciprocal or inverse to one another. Since they are inverse to one another, then, and we had this equality or identity before, we said the composition of the function and the inverse is equal, and operating upon a point gives you the unity of functions, and therefore here you have f minus 1 f of x is equal to x. So you have here e to the ln x must be x equal to x, and you have f minus 1 of x equal to x for all values of x lying in the domain of the inverse function. So this is true, is equal to 1 over x for all the x greater than 0. So you see, we do this in steps, and you can directly do this easily using your theorem. But usually students, they don't like to do it this way, because you have to have the two diagrams in front of you to think about them. But you can do them, of course, using a longer number of steps. For example, you can do it this way. Y is equal to ln of x, and you want to differentiate with respect to x. So the next step, you put x is equal to e to the power y. And then you differentiate this. You get dx by dy is equal to the e to the power y, of course. And from this, you have dy by dx is equal to 1 over e to the power y. And then you substitute y from here is equal to what? Is equal to ln x. And then you substitute e to the ln x, which is equal to x, and you get this. So here, contrary to the previous slide, we did it in 3 steps. Here we needed 6 steps to do them. Well, it depends. It's up to you to choose which. Of course, this one is easier, but the other one is also easier once you understood the theorem. Now, suppose, for example, you want to calculate the derivative of sine minus 1 of x, which is the arc sine of x. In other words, the derivative, the inverse function of the sine. Now, the function sine, we said it's not injective. Then you have to choose an appropriate interval at which the function is injective, is 1 to 1. So it shows from minus pi by 2 till pi by 2, and the range from minus 1 till 1. So the inverse function will have a range of minus pi by 2, and the interval and the domain will be from minus 1 to 1. So we want to use the theorem. So we say dy by dx at the point x lying in the domain of f minus 1 of sine minus 1 of x is equal to 1 over d by dy of the original function, which is sine y, at the point y is equal to sine minus 1x. In other words, at the point which lies at the range of the original function, of the inverse function. So here you have the derivative of sine is cosine. So you substitute at the point sine minus 1 of x. And then what you do, you have the cosine here in this region. It's positive. So you have the cosine is equal to the square root of cosine squared. And then you substitute cosine squared by 1 minus sine squared. So you have here 1 minus 1 squared of sine minus 1 of x. Again, here you have what? You have f of f minus 1 of x, which is equal to x. And you get at the end the derivative of the inverse function of the sine function. These are derivative of some of the known inverse functions. Here, the logarithm of x, as we said before, this is the Neperian logarithm with respect to the base e, the number e, so it's equal to 1 over x for x greater than 0. When it is log to the base a, you got this expression here. And then we have just calculated the derivative of the inverse function of the sine, and the arctan, you got this one here. And you may have another set of derivatives for other functions. Of course, you don't memorize them because they exist at the end of your texts. Now, composite functions. Now, composite functions, usually functions exist in the form of composite functions. You have, instead of f of x, You have f of g of x, like for example, this e to the square root of x, or sine, cosine x, etc. So how you deal with these functions? You use what you call a chain rule. Now a chain rule is the following. You have y is equal to f of u, and u is equal to g of x. So your function is in the form of y is equal to f of g of x. So what you do is the following. Here you have y is equal to f of g of x. In other words, you have a composition between f and j. So what you do, you can substitute g of x is equal to u. And you say the following. You say, if j is a differentiable function at the point A, and f is a differentiable function at the point g of A, then the function, which is a composite function of f and j, is differentiable at the point A. And what you have here is the following. You have dy by du. You use the notation of Leibniz is equal to dy by d. You have dy by dx, I'm sorry, is equal to y by du times du by dx. So what you do here, u is equal to g of x, so this becomes g dash of x, and here dy by du, you have f of u, so you get here f dash of u, but u is equal to what? Is equal to g, so you have finally the form f dash of g of x times g dash of x. And this is your formula which you shall use. This is the best way of doing it. You substitute g of x by u, and you have here to see that since y dash is equal of x is equal to f dash of g of x times g dash of x, it just means that the domain of the derivative will be the intersection between the domain of both functions, which is g dash of x, and the composition between f dash and g of x. For example, you have the following. Y is equal to e to the power x, and you want to differentiate this with respect to x. The easiest way is to have a dummy variable. U is equal to the square root of x, in which case y is equal to e to the power u. Then you use, as I said before, you use the notation of Leibniz. Dy by dx is equal to dy by du times du by dx. But du by dx, you have it, is equal to what? X to the power half. Half x to the power minus half, which is 1 over 2 square root of x. While dy by du, you have y is equal to e to the power u. So dy by du, the exponential is the same. Derivative is the same function, e to the power u. Now here, either you leave it this way, or you can go back and substitute for u is equal to square root of x. And you finally obtain e to the power x divided by 2 square root of x. Same thing. Here you don't have always to find function in the form of a composition between two functions only. You may have 2, 3, 4, etc. For example, here you have tan square root of 1 plus square root again of x squared plus 1. So here you have actually, you need, instead of one dummy variable, you may need more than 2 or 3. So what you do, the easiest way, is that you can substitute x squared plus 1 to be equal to t. And then you take all this, what's inside the square root, to be equal to v. So you have here now v is equal to 1 plus the square root of t, which is equal to x squared plus 1. And then what you have here, you can take all the square root of v to call it u. And finally, you have y is equal to 10u. So here you have a function, a dummy variable, u and v and t, and you finally wish to calculate the derivative of y with respect to x. So you do the following here, again, as if you're doing algebra. Dy by du is equal times du by dv times dv by dt times dt by dx. You can cancel out the t and the v and the u to obtain finally dy by dx. So derivative of dy by dx is the sec square, derivative of tan. The derivative of square root of v with respect to v is 1 over 2 square root of v. And the derivative of v with respect to t is again 1 over 2 square root of t. And finally, the derivative of t is 2x. And you multiply them together to obtain dy by dx. The important thing you notice here is that you always try to decompose as if you have a chain, something which is cumbersome, complicated, and you wish to entangle out, or you wish to isolate the functions that you find that are basic functions or elementary functions. Each of these functions, the tan is an elementary function. The square root is x to the n, and this one too, and this one. So you are able to isolate this complicated composite function of many, many variables. You are able to, or always, this is the way you should try to do, is that to isolate it and to write it down in the form of as many as elementary functions as you can. Now here is a theorem relating here. We take special forms of f of x. Now f of x, I can take f of x is equal to x to the power n. So you have here a composition. Gx to the power n is f circular j. It's a composite function between f, which is x to the power n, and g of x. So the derivative is equal to what? F dash of g of x. Now f dash u to the power n, the derivative is equal to n, u to the power n minus 1, where u is equal to g of x. So you get n g of x to the power n minus 1 times the derivative of u, which is g dash of x. Again, when you have, for example, the square root of g of x, so the derivative is equal to what? The derivative of the square root is equal to, the nth root is equal to 1 over n, u to the power 1 over n minus 1. This is a power function. And then you substitute u for g of x times the derivative of g of x. And finally, the derivative of the modulus of g of x. You try to memorize. You know that the derivative of the modulus of x is equal to modulus x over x. So here you have the derivative of mod u is mod u over u times the derivative of mod u of u itself with respect to x, which is g dash. These are some functions relating special cases of the function f. This is a function which is y is equal to x to the power x. This is not an algebraic function. Some students confuse between this and x to the, and they write the derivative in the form x times x to the power x minus 1, which is not true. So what you do here is that you can, you have different ways of dealing with this function. Either you take the logarithm to write it down in the form logarithm of y is equal to x ln x, and you differentiate product of two functions, or you may write x to the power x in this form. Because e to the ln x is equal to x, so this is in fact e to the x to the power x ln x is the same as x to the x. And now you apply the chain rule. You want to calculate the derivative of e to the x ln x. What you do is that you can take x ln x to be equal to u. And then you have here y is equal to e to the power u. Now you want to find the derivative of y with respect to x. So you differentiate y with respect to u, and you multiplied by the derivative of u with respect to x. So the derivative of y with respect to u is e to the u, because this is exponential function, times the derivative of u with respect to x. This is the product of two functions. So the derivative becomes equal to the product of the first one, which is the derivative of x, which is 1, times the second one without change, plus x times the derivative of the ln, which is 1 over x, and you get finally your result here. The same e to the u, which is e to the x ln x, it's equal to x to the power x times ln x plus 1. So this is the way of doing it. You have two choices. And even sometimes you can have functions in this form, cumbersome functions and complicated functions, where you have a quotient of a product of many terms divided by, for example, the product of many terms as well. The best way of approaching such problems is to transform this quotient using the logarithmic functions. So if we take the logarithm of such function, because otherwise, if you want to use the differentiation rules, like for example, the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, you always get confused and you always do mistakes. So the best thing is that you take the logarithm. Here, the logarithm of this times this divided by this is the logarithm of this plus this minus this, and this simple rule of logarithm. So we have here the logarithm of x minus 1 plus the logarithm of e to the x, which is x, because these are inverse functions to one another, minus the logarithm of this, which is 3, you got, because it's in the power, minus 3 logarithm x squared plus 1. Now you have here, you have here a composite function, and you have here another composite function. So the derivative of ln y with respect to x is equal to what? This is a composite function. Because y is function of x, and you have here function of y. So you differentiate logarithm y with respect to y. If you differentiate logarithm y with respect to y, you get what? You get 1 over y, derivative of ln y with respect to y, times the derivative of y with respect to x, is equal to the derivative of the right-hand side. Here you have a composite function, so it's equal to 1 over x minus 1, plus the derivative of x, which is 1, minus 3, the derivative of a logarithm of x squared plus 1, you can take x squared plus 1 is equal to u, so you differentiate with respect to u, so you get here x squared plus 1 times the derivative of x squared, which is 2x, and you finally obtain this form here, which is the same. In fact, all we have to do, all we did, the difference between what we have written here and what's on the slide is that we multiplied this equation by y, and y, you already have y here, and this is the final form expression for differentiation. So usually you use logarithm when you when you need to deal with fractions. Now, sometimes you have derivative of implicit or parametric functions. Now, implicit functions of this sort, cosine xy is equal to x plus y. You can, of course, here, same thing. You can substitute xy to be equal to u and proceed with the same way. Now, here we have a theorem relating the derivative dy by dx with respect when you have a parametric function. X is a function of g of t and y is a function of t. So derivative of y with respect to x is equal to what? And we found this before, we said it before, is equal to dy by dt divided by dx by dt. But dy by t is equal to f dash of t and dx by t g dash of t. So you get this expression here. You use again the same notation of Leibniz. So for example, you want dy by dx and you have x in terms of t and y in terms of t. So you get directly dy by dx is equal to d, because you can cancel out dt. You have dy by dx is equal to dy by dt, which is cosine t, divided by dx by t, which is minus sine t, to get minus cosine t. Now, sometimes you have repeated differentiation. In other words, you differentiate once and you want the derivative of the derivative. And this you need it all the time. Here, for example, this you have two functions here. And this functions here, this function is monotonically increasing. In other words, f dash is positive. And this one as well, f dash is positive. But there is a difference between the two. Here, f dash, here it was large and it's decreased. So you have f double dash less than negative. Whereas here, f dash increase is always positive, but f dash is in the increase. So we have f double dash positive. So you understand. In other words, it's like, for example, you have a velocity. The velocity, the body moves in this way, but it decelerates. So whereas the velocity is positive, but the velocity decreases. So the acceleration is negative. You have a deceleration. So the second derivative with respect to the distance is called acceleration. So you have the acceleration is negative. Here we call this curve concave downwards. And this one we call it concave upwards. These are the notation for repeated differentiation. Again here, these are notation of Lagrange, and these are notation of Newton, for example. These are notation if they are differentiated with respect to time, y dot, y double dot. These are notations. I mean, each one of them are a notation of certain scientists. But the best, as I told you before, it's better and it's preferred that you use the notation of Leibniz, because you can manipulate so that it looks as if you are doing an algebra. So these are the notation of Leibniz, and you are always free to use them better than any other notation. Now here is Leibniz theorem. This is a theorem relating the nth derivative of a product of two functions. For example, if you have a product of two functions, f and j, and they are differentiable, and you wish to calculate the nth derivative, in other words, not the first one, the second one, but for example, the fourth one. So you use a form very similar to expansion of the binomial. So you have the derivative, the nth derivative of a product of two functions equal to the nth derivative of the first times the second without change, plus nc1, the combination of n with respect to 1, which is n, times the derivative n minus 1 of f, times the first derivative of g. And you go on like this to obtain the binomial expansion, as if you are writing exactly a binomial expansion of a product of two functions. For example, here you have x cubed sine x, and you wish to differentiate it 3 times. So what you do, you write f, and you write j, and then you have f dash, you differentiate this once, you get 3x squared. And then you differentiate it twice, and then you differentiate 3 times. After that, you don't differentiate it anymore, because here the derivative is 0. Whereas g of x is sine x, the derivative g dash is cosine, and then g double dash is minus sine, and again the derivative is minus sine. So what you do, you apply your theorem. So the third derivative of x cubed sine x is equal to what? Is equal to the third derivative of the first function, which is x cubed, this one here, times the first one without change, which is this one here, plus 3 times the derivative, the first derivative. Now, the nth minus 1, which is the second derivative of the first one, which is this one, times the derivative of the second one, which is cosine x. And you keep going on like this. The third term will be 3 times 2 divided by 2, 3c2, which is again 3c1, times again now the first derivative times minus sine x, and you go on like this to obtain the derivative, the nth derivative. We wish to tell you something. It's imperative that you should watch out for functions that they look alike. For example, suppose, we have a function like this one, tan minus 1 of x, plus tan x minus 1, plus tan x all to the minus 1. The students sometimes they get confused with notation like this. Symbols used for functions, sometimes, as a matter of fact, sometimes they substitute this, for example, arctan. But anyway, this is the inverse function of the tan, whereas this is the tan of 1 over x. This is a composite function, whereas this one is the cotan function of x. So you see they are different, and each one, of course, they have a different derivative. So this one here, this is the inverse function, tan minus 1 of x, the derivative is equal to 1 plus x squared. Whereas this is a composite function. The derivative of the tan is equal to what? Is equal to sec squared. Sec square of 1 over x, because we can substitute this for u. So you get the derivative of tan with respect to u, which is sec square u, times the derivative of 1 over x, which is minus 1 over x squared. Whereas the cotan, the derivative of which is equals to minus cosec square x. So you have forms like this. These are tricky. Or you have, for example, e to the power square root of x, or the square root of e to the x. Things of this sort. The notation, you should be aware that the notation of functions you should be accustomed with at the very beginning. Also, when we spoke about differentials, the differentials are a very powerful tool for manipulating or obtaining derivative of functions. Sometimes you don't have to use the ordinary differentiation, but you can use differentials, and this is why I told you before that these expressions of dy and dx, you better use them before, because they are able to transform your calculus into a real calculus, in other words, into algebraic operations. Sometimes, for example, you have functions of this sort, for example, like x to the power 4 over 3, and you wish to obtain the nth derivative. Now, this doesn't end. I mean, for example, in the example that we showed before, you have here, for example, sine, and the other one is x cubed. So this, it might end, but this does not end, because the first derivative you get third, 4 over 3 minus 1, and then minus 2 over 3, and it goes indefinitely. In other words, it's not always that the derivative of product of function, they end. You can have repeated differentiation, and so on and so on. Now, in this lecture, we have been speaking about we have already established the derivative of the differentiability of function in our last lecture, and the existence of the derivative. This lesson, we only took special cases, which are very common, in fact, because we always encounter functions not in their explicit form, but usually either in the implicit form or in their parametric form, or we wish to calculate calculate, for example, the derivative of inverse function without having to calculate the inverse function first. So with this, we have come to the end of this lecture, and I wish you have gained some information about a special class of function which they exist in many applications. And I wish to remind you, as always, I tell you that all these lessons have been and will be uploaded to the platform of the Uniutunnu Telematic University. And until we meet again, thank you for your attention and good luck.